Okay, today I'm going to introduce a hugely important concept of stereochemistry, and we're going to begin talking about stereogenic centers in cyclic compounds. Let's take a look at the first example, methyl cyclopentane. To find a stereogenic center on ring carbons, what we want to do is draw them first as flat polygons and look for tetrahedral carbons, and this is important, that are bonded to 4 different substituents. Okay, so let's take a look at the carbon attached to the methyl group. It's labeled as C1, and here's my question: is C1 a stereogenic center? The answer is no, because we see it has a methyl, a hydrogen. Okay, those two are different, but it also has identical groups equidistant from each other, that is 2 carbons, right, that make up the rest of the ring. So no, it's not stereogenic. Why? Because it doesn't have 4 different substituents. It's got 3. Let's go on. Let's look at 3-methyl cyclohexene. 3-methyl cyclohexene. And is C3 a stereogenic center? Well, let's take a look. We see obviously methyl and hydrogen are different substituents attached to carbon 3. And if we look at the other 2 carbons attached to carbon 3, we see that they are both different from each other and different from a methyl and a hydrogen. So yes, there are 4 different substituents attached to carbon 3. So the answer is yes. We have found C3 to be a stereogenic center. Now, in 3-methyl cyclohexene, the methyl and hydrogen substituents that are above and below the plane of the ring, draw them with wedges and dashes. And what you'll see is that you actually have 2 different forms, 2 different compounds. Now this is important. You have to make the molecular models to see this and to understand this. You have 2 mirror images. Okay, so in both cases, notice you can draw the version on the left, you can draw the version on the right. They're both correct. Okay, and they're not the same. How do you know they're not the same? Make a model of each one and try to superimpose the one on the other. And you'll see what these are they're mirror images. That's a mirror plane in between them, but they're not superimposable. So a mirror image that's not identical, all right, to what it's looking at in the mirror, across the mirror, whatever, you have an enantiomer. So this is a hugely important but very subtle concept. So thalidomide, and this is a really tragic story. You can Google this on the web if you want. Thalidomide, you can see, has a stereogenic center on the carbon attached to that nitrogen, and it has a mirror image. Right, there are 2 mirror image versions of this that aren't the same. So there are 2 enantiomers of thalidomide. One of them is a terrible poison, and the other is just an anti-nausea drug. And years ago, back in, I think it was the early 60s in England, many people and infants, I believe, died because people weren't aware of the difference in the enantiomers. So the take-home message here is, by changing from one enantiomer to another, you have a totally different compound, even though they look the same. so many biological molecules in biologically active compounds have stereogenic centers like these on rings. All sugars. And there's Taxol, which is a very important and popular anti-cancer drug. And you can see how many stereogenic centers does Taxol have. Just count the stars. Make sure you go over the stars in Taxol and the stars in sucrose, and that you're convinced that every starred carbon there is stereogenic.